name is Milan Wils, so the ref is yours.
All right. Is this better? Yeah? Okay, great. So good afternoon, everyone. Today, I will be talking about the impact of calibration uncertainty on supernova searches mostly, but also briefly, I'm going to talk about the possible impact that it could have on parameter estimation. So the past few days, you've already heard a lot about different uncertainties that come into supernova modeling. There is the microphysics that can have an impact. There's the resolution that can have an impact. There's progenitors that can have an impact. But so now I thought, let's give a presentation about another uncertainty, which comes from the instrument itself. So let's get going. So the first part, I'm briefly going to explain what detector calibration actually is, because I don't know if everyone's familiar with it. So most of you probably learned about how an interferometer works the same way I did, where someone tells you there's a laser beam going in one direction, laser beam the other direction, space-time gets stretched, and because it gets stretched in a different way, your interference pattern changes, you measure that, and you have a gravitational wave strain. Now, when I first started working on this project, I realized that this is not actually what happens in the detector, because this could happen if you only look at the top part of the diagram. That's a situation that you know, where the C block just tells you, okay, this is some sensitivity of your photodetector that measures the interference pattern, and then I have to compensate with an amplitude factor, and I have my strain. But it turns out that this function itself already is not just a flat function. It has different parameters, and it has a shape in frequency, so you have to account for that. But then additionally, there's another thing that people have to do, and that is actually the detector, we want to keep it in resonance. So what we do is that we measure this interference pattern, the strength of that signal, and then based on that, we pass that through a digital filter, which is designed by instrumentalists, to calculate some actuation signals. And those actuation signals are then used to push the mirror back to its equilibrium position. So actually, in the interferometer, the mirror is constantly being pushed to this exact same position. And that gives you this feedback loop, which you can model by a certain response function, which I call R in this diagram. And so the problem is we invert this function with an estimate that we have of this model, but we don't know this model perfectly. And that is something that we have to account for whenever we do data analysis with gravitational waves. And the accuracy of that is in the order of 1 to 10%, depending on which frequency you're looking at or what time in the observation period. And so here you can see a few examples of what these uncertainties can look like for LIGO, where this is a graph for Livingston. And so the way this is generated is that in certain periods when the detector is not being in observational mode, there are being hardware injections are being done to actually induce a movement of the mirror, and then that response is measured through the pipeline that you saw before. And based on that, there's a bunch of parameters for these transfer functions C and A that are being fitted. So these are physical parameters of these actuation functions, but also some parameters to model the electronics that are involved. And so this is one part, but this is only something you can do when the detector is not in observing mode. A second part is that when the detector is in observing mode, there's also hardware injections being done at certain frequencies. And then we can have a measurement of whatever residual calibration error is still left. And that is fitted with a Gaussian process regression. And if you combine the data from these two, you take draws from both samples, the posterior distribution from the actual parameters of your model, and then this Gaussian process regression, you get uncertainty curves, which looks like this. And one thing that is already important to notice here is that the left side, for example, is a plot from the engineering round 15, where you can see that the uncertainties can be fairly large, especially if you go to the very low or very high frequencies. Then you get uncertainties on your strain of the order of 10%, which is quite large. But then if you look further in the observing run, you can see that actually in the later stages of O4A, this uncertainty is very, very well controlled. And this is an argument that I want to bring to you all, is that we have to look at calibration errors and the impact it might have. And it's not because it's negligible in one time period that it will be negligible in another time period. So what has been done in the past is very often this has been modeled, this calibration error, as just time jittering and some amplitude scaling, which is something you can definitely do if you have a narrowband signal. because then any spectrum that you would have with a calibration error is only relevant in this narrow band where you can model it just by a phase and an amplitude. But as all of you know, especially after the presentations of yesterday and today, gravitational wave signal from a supernova is not exactly a narrowband signal. So we really have to take into account the physical shape of this uncertainty. All right, so let's do exactly that. And I will be looking on the impact that this calibration uncertainty has on the coherent waveburst pipeline. And the setup is quite simple, actually. So what we do is we interrupt the flow of coherent wavebursts when we're doing injections to test the sensitivity. We take all the injections that are happening, and for every injection, we draw a different curve from this distribution, apply this frequency-dependent scaling, and then re-inject it into data. And then we check between the two runs what the difference actually is in sensitivity. So first, a note on what you can actually expect the influence to be in the pipeline. So this calibration error, it is different in each detector. And if it is different in each detector, what you're actually doing is you're changing the coherence, you're destroying the coherence of the signal between different detectors. And for a pipeline like coherent wavebursts, as the name suggests, it depends on the coherence of the signal. This actually means that there's a part of the signal that will now lie in the null space, so it doesn't align with the antenna patterns of the detector anymore. And if you would look at 2G detectors where you can have SNRs maybe of 40 or somewhere in that range, and you have calibration errors in the area of 10%, your residual SNR is around 4, and this is even already a high estimate, I would say. So you can expect the impact to be relatively low because this SNR 4 signal is not really distinguishable. But then if you go to 3D detectors, you can get SNRs of up to 100, and that means that the residual signal, which is created by this distortion, can actually be significant, and it's clearly visible that it's not aligning with the noise anymore. So a few examples here. I did some injections with some curves from the third observing run, where I looked for some of the worst phase errors that you could possibly have. And then on this graph, you can see on the x-axis, you see the rho value, which is this likelihood ratio that Michele already mentioned this morning. And in limit of high SNR, this corresponds to the reconstructed SNR of the event. And then I plot that ratio with the injected SNR of the waveform. And I compare that to the thing on the y-axis, which is the same quantity, but then in the case where calibration errors have been applied. And what you see is that actually for most signals, most of the events that were injected, this is directly on the line. So you can see that actually the reconstruction is happening equally good. But then there's this small group of injections which lie slightly below the line and have a difference which is almost 10% in the reconstructed SNR. And if you look at what's happening in those injections, you can see that actually the number of pixels in the reconstruction is decreasing. So what happens is that this slight change in coherence actually means that part of the pixels that you're selecting when you reconstruct the event and when you're calculating the likelihood value of the event are not being selected anymore. They just drop below the threshold, and then the clustering algorithm does not take them into account. And then there's a second effect, which for me was the most intuitive one, is when you go to really, really high SNR, which is what you might have, for example, for the third generation of detectors. And then you can see the same quantities on this plot, but you see that for the very high SNRs, where you go in the direction of 400, you see this curve getting a slight bend, which means that indeed, if you apply calibration errors, you're not recovering all of the injected SNR simply because the signal is no longer coherent. Then that's what's happening internally in the pipeline. But what we're most interested in, especially right now, when we're still placing upper limits, is actually what is the impact on the detection efficiency? Does this change how much events we can detect and up to what distance? And it turns out that when we tested this for Supernova 2023 IXF, this difference was on the order of 1%. And even you can see in this graph, it's not always a negative effect. Sometimes it's positive. This is just because it's so small that this interacts with the noise. And so, yeah, if you look at this, you can sort of conclude that for searches, it will probably not be important, simply because the point where you see the impact is with a very high SNR, but those events are detected anyway. So for detection, there's no problems expected. So let's then go towards parameter estimation. So here we did a quick test by looking at the core bound signal using the Abdikamalov catalog. And I'm using some of these curves that are generated by the calibration group. So I'm just sampling from these 10,000 curves, applying the calibration error, and then checking how consistent the original waveform is with the effective waveform. And what you see is that the distribution on top there is very, very narrowly concentrated towards 1, which means the waveforms are almost identically the same. If you would do match filtering with them, you would basically not lose any calibration, any signal-to-noise ratio. And the next talk by Claudia will be about estimating the ratio of the rotational energy to the total energy, this beta parameter. And there's a model for that where there's waveforms generated with which you can do this parameter estimation. And the waveforms from this model, if you compare them to the actual waveforms from simulation, the fitting factor is centered around 0.95, which is much, much smaller than the effect of calibration. So you can expect here that there's not going to be too much influence. So I also created one example here to show you what happens if you look at it in a time domain. And there you can see maybe a slightly bigger effect than you would expect based on the fitting factor, which is that the relative magnitude of these peaks can change by quite a bit, a lot more than this 0.001 factor in the fitting factor. And so this, if you would try to do parameter estimation with a very, very accurate model, which we currently don't have yet, then you might see some biases here because you're not taking into account this calibration uncertainty. Then these rapidly rotating waveforms are not the only thing that we're interested in. So I also have some arguments for when you would look at parameter estimation, for example, on the high frequency feature. But there, when you have some amplitude errors, you will see the same amplitude errors over the whole time series. It will just be a function of frequency. So this is, of course, not going to fundamentally change the shape of this G-mode, and so you would not expect there to be much influence on parameter estimation. What is maybe more interesting is when you look at the phase error, because the phase error is more or less constrained equally for all frequencies. But a phase error at a low frequency will correspond to a much, much higher time jittering. And so you can see this formula here is that if you would have a 10% calibration error around 20 Hertz, which is a very conservative estimate, then that would correspond to roughly 1 millisecond of jittering. And so if you would look at the effect of what you see on the spectrogram, it's basically a small shift at low frequencies, which could impact your G-modes or high frequency content slope a little bit, but that effect is of the order of 1%. So this is still lower than what we can currently do when estimating this slope. Finally, we have a similar picture for the SASE. I plotted here 2 examples of actually the reconstructed events in coherent waveburst, where you can clearly already see that these features, they don't change shape much. By eye, you can basically not see it. And so when you would try to estimate the presence of SASE, I added the formula here. And if you want the details, please listen to Vicente's talk on Friday. So you can expect that this ratio also will not change much. But if you would have sharp features, which currently are not really included because of this Gaussian process regression in the estimate of the calibration uncertainty, then you could perhaps see a small shift in this constraint of the estimated frequency of the SASE, simply because part of these pixels might drop out when you run coherent waveburst. So as a final conclusion, we now have a plugin that's for CWB, which can actually use realistic calibration errors and just marginalize over the uncertainty, basically when you do your detection efficiency calculations. But for detection efficiency, the impact is probably negligible, as we see with the test, and this is exactly in line with what we expect. But for parameter estimation in the future, it might be more important, especially if we go towards precision tests of this rotational parameter. Then if you have 3G detectors where the signal-to-noise ratio is extremely loud, we might get into trouble. Right now, it's not a problem, but we have to keep an eye on it. And finally, for future work, so one of the things we still want to do is we want to check if these sharp features would actually have an influence, because right now they're just not included in the calibration uncertainty. And also, we would like to run the full pipeline from injecting, having injections with calibration errors, running coherent waveburst on it, and then checking if the SASE estimation or the G-mode slope estimation differs because there might be some pixels that are dropping out. So that's it. Thank you for your attention.
Thank you, Milan. Some time for questions?
I guess if Beetlejuice blows up tomorrow, then we could have something in the extremely loud category now.
Yes.
So, like when we want to use a bit of gravitational wave data to search for a supernova that's been observed electromagnetically, then we put in a request to, you know, the LIGO people who work on the data quality and the calibration and stuff, so that, you know, the data is usable for the search. And so then they ask me, because I'm the burst chair, like, what kind of calibration do you need? And I've been telling them, we can just use the crappiest calibration for the search, but then if we actually make a gravitational wave detection, we'll probably want some better quality calibration before we make some astrophysical statements. So do you agree with what I've told them, or should I be telling them something else?
Yeah, I would agree with that statement. Also, the crappiest calibration that they would be willing to give, I think, is of the order of 10%. So that definitely is not a problem for us for detection. But then for parameter estimation, yeah, we should be careful, especially if the SNR is so loud, because then we don't even, I don't know if anyone knows what coherent wave bus is going to do when you have SNR of 500 or something.
I don't know if it can be said publicly, but when the first pass on GGI was much worse than 10%, then they put it back together. Marco can tell the story later on. But it's good.
Any other question? No, I have a question myself.
Yeah.
Do we expect that the model for the calibration will improve in the next future? As difference between AR15 and the 04?
Yeah, so the thing is, let me go back to the very beginning. So you're asking if this will improve even further. I wouldn't expect this to dramatically, like it wouldn't keep increasing at this rate. So what usually happens is whenever you have an upgrade, that's right after you have this engineering run. Mm-hmm. So at that point, people are still figuring out all of the issues that they get because some things change to the detector, and that's why you see this big improvement. Mm-hmm. Of course, if you go to 3G and people want to do tests of VR, then this might not be acceptable yet, and then people would have to do more work. I once saw a quote by Jeffrey Kissel in some presentation where it's like, yeah, sure, no problem. We can get this to 1% or 0.1%. It will just take an incredible amount of manpower and bookkeeping. Okay. So I think it's more a resource problem than a physical problem.
Okay, thank you. No more questions. Thanks the speaker again.